All right, so I'm from Portland, land of pasty skin and moisture. So I would first love to appreciate you Floridians bringing in the clouds and the rain. I feel like it was for me, and I'm very comfortable, so thanks. So what I'm going to talk about is distributed patterns in Ruby. I feel obliged to mention again that I work at Basho. I also have a couple books out, 7 Databases in 7 Weeks, and more recently a little React book that's free to download from my GitHub account. And I'm going to post all these online, so you don't need to feverishly write anything down. But my GitHub account is GitHub Kodoroshi, little React book. And you know, I do tell people that if you buy the book and don't like it, I won't offer a refund. But what you can do is buy 5 more copies and burn them, and you will have taught me a valuable lesson. And that'll show me. So this artist, Rucher Urf, I am kind of a fan of, and attempted to do a sketch with his left hand. He's a right-handed artist, attempted to do a sketch with his other hand. And this is what he ended up with. But it's interesting, you can tell that he had a hard time holding the pen. His hand isn't strong in that way, and it's not anything he's practiced, but you can tell that this is not actually the work of an amateur anyway. You can tell the character's female, the face isn't bad, the girl on the far side is exacerbated with the classic anime sweat drop. He clearly knows what he's doing. The skill wasn't in his hand, it's in his head. He knows what to look for even though he is an adept. And the reason I wanted to point that out is because you can glue together toolkits, but it's not going to fix an ignorance problem. But there's a flip side to that. Just like with the artist, if you know what you're doing, you don't have to have necessarily toolkits to stand on. You can do a pretty good job on your own. You understand what it is, and then you pick the tool to solve the problem. You don't just pick tools and cargo culting and look at other people that have done similar things and then try to clone that and say, okay, now my system is going to be like Google because I copied what Google did. But what I'm going to talk about is distributed systems in particular, and this is one of my favorite definitions of a distributed system. I like this definition because it specifically noting the emphasized words because they're all important. If you take any of these bolded terms away, you don't really have a distributed system anymore. And Rails users take special note of this definition because if you have a bunch of autonomous nodes that are or servers that are running and they're all taking requests, but they're not communicating with each other, you don't really have a distributed system. You just have an array of servers that are sharing information. Now, I also want to notice though is distributed systems are great. I mean, we all understand, I hope, the reasoning why you would want a distributed system. It's a great way of scaling horizontally. There's a limit to how much you can scale vertically and having one server that gets bigger and bigger and bigger. But it's also really great for availability as well. You know, if one of those individual servers go down, your entire system can be up and running. And as I hope you understand, that the more servers you add, the likelihood of any single one going down goes up exponentially. I mean, it's just math. It's like if you've got if you've got a 0.01 chance of any server going down, and you have 1,000 servers, the chance of any one of those servers going down is like 60%. I mean, something's going to go down. But there is a dark side to this, and the CAP theorem, which is generally understood as a database problem, but this is actually just a problem with distributed systems in general. Who all is familiar with the CAP theorem, by the way? All right, okay, I am going to explain it, so I'm not just going to skip over it. So what the CAP theorem says is, if you have a distributed system, you must be partition tolerant. So P is not an optional thing if you have a distributed system. But you can only have 2 of these 3 things. So if you have a distributed system, you can be partition tolerant, you have to be, but you can either be consistent, meaning the entire system will return the same answer to any request, or you can be available, meaning that every time you request something from the system, you get a result. And I think it's pretty easy to explain. So let's take these 3 guys in the front row. And let's say that you guys are nodes in a distributed system. And then I, as a client, come to you and I say, hey, A software client, not a customer paying client. I come to you and I say, okay, the word of the day is jump. So now you all know the word of the day is jump. Now you get up, you go to the restroom. And then while you're gone, I tell you guys, hey, guess what? I changed my mind. The word of the day is now leap. Now somebody stops you in the hall and says, hey, what's the word of the day? You have a choice to make. You know you're partitioned from the rest of the system. So you can either remain available and choose to answer the question, say, hey, the last thing I knew, the answer was jump, not knowing that I changed it to leap. You are now inconsistent. This system is an inconsistent system because if I ask you versus you guys, I get a different answer. Or you can just choose to not answer at all and say, you know what, I don't know. You're not available anymore, but you haven't destroyed the integrity of the system as far as consistency is concerned, because you're not giving me a different answer from them, you're just not giving me an answer at all. And so that's the CAP theorem in a nutshell. You pick one, you get consistent or available when it's distributed, but you can't possibly have both. It's a physics problem. And just as a side note, I am telling you with some semblance of authority that anybody who claims that they have beaten the CAP theorem or that it doesn't matter or that they can deliver both consistency and availability, I'm not going to say that they're intentionally lying to you. Probably they just don't actually understand the implications of what they're saying. So I don't know how in the world these end up here. All right. So we're going to talk distributed patterns. These are the distributed patterns that we're going to write. Distributed hash table, message patterns, vector clock, Merkle tree, and MapReduce. And I picked these for a couple reasons. One, because they're actually really easy to write in Ruby. And we're going to write some now. And two, these are actually a lot of the distributed patterns that underlie many distributed systems. React is the company Bash I work for. We make the React database, and we use all of these patterns. But we're not the only ones. Cassandra uses them. I mean, you guys have probably seen MapReduce before. Almost all NoSQL databases supply some type of it. Vector clocks are another common one. Message patterns, that's not a data structure. That's just a pattern of how do we communicate between servers. And everything that's distributed is going to use some type of message patterns. But let's start with a distributed hash table. Distributed hash table, also called a consistent hash, distributes data evenly. But the most important part about it, unlike sort of a classic hash table that you're all aware of, also, hash in Ruby, is there's minimal disruption when nodes are added or removed. And I'm gonna show why or how this happens by implementing my own hash. This is just a really naive hash implementation where I store the number of nodes and then I give a block of buckets in my array. I'm sending requests to those nodes. And then my hash is just SHA-1 and it gets put in the array. These are the important parts here. Is I have my array, however many nodes I have. If I have 4 nodes and I want my spread to be 1,000, meaning that each node can handle 1,000 values, I'm going to have 4,000 array. And then they get just hashed just as you would in a normal hash algorithm. Now, does everybody understand the concept of a hashing algorithm? Basically, we convert an object into a number and assign a hash to a bucket. That's it. But there's a problem with our standard hash implementation. So here, say I start with 3 nodes. Now, the number you hash to is always going to be much larger than the range of your array if you're using anything like SHA or something like that. So what you do is you just do a modulo on it. And so in this case, it might convert to the number 4, but I do a modulo 3 because I only have 3, which puts it in bucket position 1. So it's 0, starting counting zeros, so 0, 1, 2. It gets put in B. So this is where my value will live on node B. But if I add a node to it, now I do D. My number 4, it still hashes number 4, my same object. Modulo 4, oh, now it's 0. Now it gets put here. This is a problem when you have a distributed system because if I have a whole bunch of data sitting on one server and I want to add a new server to my collection, I now have to take all of that data and move it, which is ridiculously expensive. So I made a little program with my naive hash. I said, okay, each node can hold 100,000 elements in it. And then I just said, okay, I just put a bunch of values. Sorry, no, I put 100,000 elements in my array that goes from A through J. So I have A through J nodes, so I have 10 nodes. I add node K, and then I try it again. And I want to count how many times, if I tried to hash this value, it would miss the original bucket that I put it in. And my miss rate was 90%, meaning that 90% of the data in all of my nodes is now stale and worthless. So what consistent hashing does is, rather than having very discrete buckets where things live, it instead will map nodes. So we've got the red nodes so we've got A, B, and C. It'll map them to a position on a circle. And what's nice about this is, as I add and remove nodes, so say I got rid of C and I added D, the only values that, in this case, so I've got values 1, 2, 3, and 4, the only things that are stale is the range here between the C and the D. So 4 is stale, and that's it. So our really simple, consistent hashing implementation, we initialize a ring. I mean, I'm kind of cheating here because the ring I'm keeping track in a hash, but whatever. I mean, that's actually not important, because what we're doing here, we're not trying to make an efficient hash that sits on a single server. We're trying to minimize the amount of thrashing that goes on when we add and remove nodes from our network. So what we do is we'll add a bunch of these nodes. The hash implementation is exactly the same. It's still a SHA-1 algorithm. But the most important thing to note here, I guess I have a better slide that shows it, is our node. We have a sorted list of nodes. When I want to know, hey, I have this key. Before, in our picture or circle, the keys would have been 1, 2, 3, or 4. I have this key. Return me the name of the node that this should live in. And what it'll do is it'll iterate through the nodes, and each of these nodes is responsible for a range of values, and it'll just say, hey, node A, are you responsible for this? Are you responsible for this? Are you responsible for this? And it actually, so, in this example, I created this consistent hash. I should also mention too, don't worry if the code, like every line of code, doesn't necessarily make sense, because I have all of this code available. You can download it and play with it at your leisure. I just want to go over what it does so that when you're looking through it on your own time, this will make a lot more sense. But the important thing is, so this is actually the exact same test I ran on my naive hash. The difference is now my cache miss isn't 90%, it's 7% when I added an extra node. So we're clearly on the right track. But what we have with this sort of implementation is a smooth, continuous hash where nodes can live at any point on the ring. But there's a clear problem of balance here. I mean, you can even see it just by looking at it. It's like over there, it's like you've got A, B, and D all kind of clustered up here at the top. What you really want to do is balance the ring so that you have, if you have 2 nodes, you have A and B. If you have 3 nodes, you have A, B, and C. If you have 4 nodes, you have A, B, C, and D. You want it to balance around the ring. So there's no real enforcement on how many keys we also rehashed when C became D. We only have the average case. And obviously, B owns far more key space than A or D. So an alternative form of consistent hash, and this is the one that we use with React. This is the style that Cassandra uses. Almost all real-world implementations use this form. The only reason I wanted to show you this form is because if you ever look up anything on Wikipedia about consistent hashing, it goes on and on about this, and that's because this was sort of the first take. This is the real production consistent hashes that people actually tend to use, and they have a fixed number of key space partition where a partition is a range of keys, and then we just assign each partition to a node in a round-robin fashion. And the benefit here is balance, so you're getting relatively even distribution of keys, and more importantly, adding and removing nodes can keep misses to a reliable amount. So see, originally here, I had these nodes, I added a third, and it's hard to see the colors, but they do alternate from light yellow to light green to light blue. I didn't color it, but so hopefully the red is a little more obvious. But now I add, and I'm still relatively balanced around the ring. And the whole thing is about keeping these values balanced. Now, you might say, well, what's the catch then? Why don't we just use this as our consistent, why doesn't everybody use this as a consistent hashing algorithm all the time since it's so superior? Well, there's a downside, and that's you're limited to how much you can grow. However many partitions you can have. In this case, we have 32 partitions. You can't add more than 32 nodes. You're just sort of stuck at that point. You can't add a 33rd node with this without completely repartitioning the entire ring and then rebuilding, and then you're sort of back to where you were. Now, that said, the good news is, as a practical matter, that actually doesn't necessarily happen because you can have as many partitions as you want and still remain balanced. So you could have 1,000 partitions for 10 nodes, and then you can add up to 1,000 nodes, which you probably won't get to anyway. And once you're at that size, then, all right, bite the bullet and just rehash it. I'm not going to dig through the code of that one because it's a little hairier. You absolutely, I would say, look through it at your own. Now, the misses is a little worse on this than the other one, but that's just the random data set I picked. But the thing to note is this is pretty close to the number because I have 11 of these. Since I have 11 of these nodes, this is about 11, or 1 divided by 11. It's pretty similar. It's kind of what you would expect on a rebalance. So there is one more thing that we should keep in mind with this special kind of consistent hash, and that's to build a preference list. And in short, a preference list are the n successive partitions that you wish to replicate an action. So if you have the key foo, we have down here, which maps to node B, or node A in this drawing, the preference lists are the next n-1 nodes. So since, in this case, if we set n to 3 in our preference list on foo, we would get B, C, and D. I drew this weirdly, I don't know. So A, B, and D in the picture, but B, C, and D in the example up here. And this is really important. This is how we're going to get high availability, because it's one thing to consistently hash a value across a ring, but if one of those nodes goes down, you have lost you've lost that segment of your data. But if you've replicated it, you now have much higher availability. In this case, if A goes down or B goes down or C goes down, you still have 2 copies of your data. So this preference list is something we're going to use later on, but it's definitely a very important piece of this. Now, this is just a simple object. It contains a value. I convert it to JSON. I'm able to serialize and deserialize it. The reason for this serialization is when we add our messaging, our network piece, that's how these individual servers are going to be able to share data. They're just going to serialize it, convert it to a string, send it to the next one, and then deserialize it. Now, this is our node class. And what it does is it manages the hash ring as well as a hash of data. Remember when I had said before with our hash ring implementation, it didn't matter that we had a hash in it because efficiency wasn't really that important. All it's for is looking up. If I have a key, the entire reason for this consistent hash is only to say, what node are you supposed to live on? It doesn't store data. It just tells me where it's supposed to live. And so with this node implementation, does actually store the data. This is what's going to live on any particular server. So does everybody get that? Okay. And so I'm just creating a standard put and get interface where I have my node, I have my consistent hash ring, I contain my data in a hash. I gave it a name just so we can tell nodes apart. And then all I do is I use my ring and I look up the node by key and say, hey, is this you? Am I in the right place? If so, store it. Same thing with get. Am I in the right place? Okay, get it. And here's a sort of more truncated view. These are the more important aspects, but it's the same code. It's pretty simple. You get a value, you put a value, and it only stores that version locally if it's the correct node. Simple as that. And here we run it. We've created 3 nodes. See, I gave it a name, A, B, and C, and then I also sent in the ring. So each of them are aware that there are rings, A, B, and C, and that's how they know about each other. I put a value in node A, foo. It returns nil. Why? Because it was the wrong node. It doesn't belong there. I put it in B. It returns bar. That was the one that I put it in, then I got it, and it got me bar. That's what I expected. And then I tried to do it with C, exactly what we expect. C was the wrong node, so it doesn't actually store it. So there are limits to how useful that is because I just ran these all on one server. What we need to do is we've created our consistent hash which can route messages to all nodes. But before we can actually use it, we need to ensure that every node is on the same page, meaning that every node needs to know the state of the cluster to ensure routing is done as expected. So we're going to play with a few messaging patterns. Request reply. It's a pattern that everyone is intimately familiar with, anybody who's done any sort of networking whatsoever, ever used the web or whatnot. Publish, subscribe, and then pipeline is another one. We'll go into detail of what all of these actually mean, but what we're going to use request reply for is we're going to query and we're going to use it to query nodes. Each of those nodes is ultimately going to become a server that runs on its own server. And the idea is that you can query one node, and if it's the correct node, it will return you the value. If it's the wrong node, it's not going to just say, I don't have that value. What it's going to do is it's going to forward that request to the correct node. Because it has a consistent hash, it knows where the real value lives, so it's just going to make another hop on your behalf to get the real value and then return it to you. So we're going to use request reply for both of those cases. I'm using 0MQ as an implementation. It's a little higher level than socket, much lower level than middleware. I love it. Who's familiar with 0MQ here? If you're not familiar, I highly recommend taking a look. It is one of my favorite pieces of work, but one of my favorite things is it's entirely transport agnostic. When you say, I want to connect to something, you will tell it in what way you want it to connect. You can do in-memory, inter-process communication, TCP, multicast, all these different kinds of communication, but your interface is exactly the same. All you have to worry about is the pattern. Am I doing publish, subscribe? Am I doing request, reply, pipeline, or whatnot? 0MQ handles buffering and framing for you, unlike if you're doing raw sockets where you've got to deal with that yourself. It's message-oriented, not byte streams or anything like this, although you can do that if you want. But for our purposes, this is all an implementation detail anyway. I'm just using this to simplify the code. So request reply, I'm not going to spend too much time on this. I think, again, we all understand what they are. They're bidirectional. You send, receive, send, receive, send, receive. That's exactly what request reply does. In 0MQ particularly, a request does round robin, and reply is the last peer outgoing strategy. Messages come in, messages go out. As Bill O'Reilly says, you can't explain that. So here we create 2 threads. We start them both up, a server followed by a client. This is just a simple 0MQ script. You can forget what we did before. I'm just giving an example of what 0MQ would look like. We create a socket, 0MQ reply socket. So this is a thread. This thread do stuff is just, I just made a little, if you look where I say require threads, include thread, if you want to download the code, it's literally just, it just takes a block and then it just runs it in a thread after you call join threads. So I'm creating a little server here built to do replies. And all it does, it just does a while loop and then just waits for the receive of anything that comes through through TCP in port 2200. If the message contains put in the payload, then it just replies, hey, I called put. Then it creates another thread, which is a client, and then it connects to this exact same TCP port as you would with a client, and then it'll send put foobar, and then request, get the response back and output it, and then it'll do it again. And this is exactly what it looks like. We've got our server here, we've got our client here. It sends it to the server sends back, hey, I called put. And here's what it would look like. Yeah, that's it. it's not magic. But the important thing is the fact that I was running them locally is almost irrelevant. If I could easily put these on two completely different machines. Now, this is a little services module that I made. The important thing here is, and you don't need to really pay attention to this, and I highly recommend don't do things like this. If you're kind of a big, Ruby nerd, you might immediately see the horror of this, because what I'm doing when I create a service is I'm getting a request, and then whatever the message is, I assume it's a function of that name, and then I'm just calling it and sending the payload to it. So yes, you could send a message and say delete, and it would delete and whatever. But this is a really simple, sort of straightforward way of doing this, because now for my put messages, I only have to implement a function called put, and for get, I just have to implement get, and MapReduce, I implement get MapReduce. So yes, evil at the side is very evil. Don't do this stuff. Normally this would be a giant case statement, but just for sanity's sake, I'm simplifying it. So that's where it's doing this. And if method missing, if it doesn't have an implementation, it'll just return, say, hey, I have a bad message. I don't know what that was for. So this was my services module. So we go back to our node that we wrote, and we add a couple things. We include the threads thing, obviously. A configuration file, which is just a simple file that'll contain the name of each of these nodes, because I don't feel like typing it in every single time I start up one of these nodes. It's just something that would live locally with the nodes, and then also the ports that they own. But more importantly is this including services. So I start up a service, and my configuration, as I said, it tells it what port it needs to start up. And this remote call implementation, remember when I said that if the current node doesn't actually contain the value that it expects, I forward it on to the one that is right. That's exactly what this does. This name is the name of a node, and this message is the message that it got. And so all this does is it connects to the remote node in exactly the same way that a client does. It just connects to the remote node, it sends the message, gets the request, and then it will presumably forward it on to you. So here's what we do with put. So here's my put function. It will send the socket that it gets from do-put, but this is where the real work happens. All it'll do is this is similar to what we saw before, right? My do-put says, hey, is this key correct for this node? If it is, store it. But if it's not, forward that request on to the node that is actually responsible for storing this data. Oh, and this is the config file makeup that I was talking about. So this is what I do. I start a node as a server, give it a name, whatever argument list, whatever argument I give, that's the name of this one. And it stores, okay, so it also sends in say, hey, my ring looks like ABC. And then this is what my client looks like, where it then connects, sends 1,000 requests to this one node, and then receives 1,000. And then that's how I start it up. But it's more interesting to look at, I suppose. So we're starting up A, B, and C, and inserting values. And if you notice, what I did in the client was connecting to A only. The client was only ever connected to A. And A then forwarded on the correct values to B and C, or if it was correct on A, then it would return it itself. So that's when you get this message where it says B get key. What it's doing is it's forwarding on to B, or it's forwarding on to C, or if it just gets it, then that was the correct one. And it may seem a little slow, but I mean, that's because we weren't doing any sort of like fancy connection pooling or anything like that. But what we've done so far is actually pretty amazing. With a very little bit of code, we've created a balanced key space. Clients can connect to any node. They can distribute objects across node, and the request response from any node will forward to the correct one. So it just doesn't matter what nodes we connect to, which is what you like, which is what you want on a distributed database. Again, we're talking about high availability here. So your client can easily say, okay, I'm going to ask A what the value is. Oh, A is taking too long. All right, fine, connect to B. And it's this sort of classic failover scenario so that you can get responses as quickly as you want. All right, are there any questions so far? Like, sir?
So if stuff on A is only on A and A goes down, how is anything more available?
That is an excellent question. And remember when I talked about the preference list, where it replicates? We haven't implemented it yet, but we're going to very soon. And that's an excellent question, because that should probably be one of the first things going through your head, is we haven't actually saved ourselves anything in availability yet. Sir?
I don't know if this is stating the obvious, but it seems to me that if you're doing something like test A, and if it's taking too long, I try B, try C. If it's taking too long because some slowdown in messaging or whatever, and then you start duplicating it on B, maybe you get a nice message that overwhelms everything.
Yes. And we're gonna deal with that situation as well. But there's one really big problem is, if you noticed in our implementations, when we started up the node, we had already hard-coded that nodes A, B, and C already exist. So why not use another message, pub sub? In this case, we're going to go a little off script. This isn't actually how React does it, but I wanted to give an instance of pub sub. What we're going to do is we're going to elect one leader to manage the publication of ring changes to all of the other nodes, so that when a new node comes in, it can then inform the rest. Normally, you don't actually want to do it that way, because as soon as you do leader election, you've created a single point of failure, and you're back to where you started with the ability to lose availability. So in this case, we're creating a function called coordinate cluster, and all it does is see. This is why I absolutely love ZeroMQ. Look at this. ZMQ pub. I've just created a publisher in exactly the same way that I would create the request reply. And so what we do here, and this is the important part of the code, is whatever the ring says, we send that out to all of the subscribers. That's all we do. Everything else is just priming that change. Track cluster, this is the opposite side of it. These are the subscriber. We create a subscriber socket. And we subscribe to any message ring from the port that the publisher lives on. And we will just accept any change that it gives us. And we will change the cluster. This was a function on our consistent hash that will just update the rings with the number of nodes that we've been given. But this is what it looks like in pictorial form. Here's the problem is, with a straight up pub sub, that doesn't really help us, because when we add a new node, that original, whoever the master coordinator is, has to know about it. So we, again, use request reply. So we're going to add a little reply socket here that will just sit and listen. If a node joins, it'll add it to the node. If it goes down, it'll remove it from the node list and then send out a response to, or send out a publication to all of the subscribers that, hey, the ring has changed. Oh, and then informing the coordinator. This was, remember, so here we had when join happens, when down happens. Same thing here. When we start up a node, we want to inform the coordinator that our join has occurred. When we close it, we want to inform the coordinator that the node has gone down. And then here's our inform coordinator. It just is a standard request reply setup, but just to the coordinator node. Yeah, and then this is if it's the leader. So this is we're passing in a Boolean that says if it's the leader, make it the coordinator. If it's not the leader, track the cluster. And if you're not the leader, then you are capable of informing the clusters that you've joined on start. So let's run that. I'm not typing here, by the way. I'm not doing this. There's way too much for me to try and do live, but I did actually run these. All of these are absolutely true. But what's interesting here is, as you see, it got the message that the ring changed as we added B and as we added C, and they were all informed of the rings changing. And then finally, I shut down the rings, and then it did this. It did them in reverse. I took down B, then I took down C. So, awesome, perfect. Leader node broadcast changes state. All the nodes inform the leader state. But what if a node dies? If a node goes down still, as you had asked, we lose all the keys in that partition. The obvious answer, replication. Now if you're familiar with Cassandra or anything like that, NRW values. N is the number of nodes you want to replicate to. R is the number of nodes that you want to read a value from when you do a read. You have the option of reading from any number up to N. W is how many writes have to be successful before it returns to the client and says, hey, I was a success. It could be 1 if you want to be really fast, or you could wait for all N's to write if you want to be pretty sure that the write has been successful. So these are the NRW values. N is the number of nodes replicated to. W, in this case, since I set W to 2, it writes these 2 grade ones, but it replicates in the background to this one. But it has responded before that replication has occurred. Same thing, R equals 2. I read from any of these 3, so I read from 2. And the first 2 to respond are, those are the ones that you get the result from. So I'm going to skip over this eventual consistency because, wow, we are really running out of time. If anybody really wants to talk about eventual consistency after the fact, but I would be happy to discuss it. So here's what our replication does. We are adding this replicate into our put. See, do put is the function we're calling. Replicate. I created this special command, put 0, because if you noticed, all of our commands had the number of nodes. So it's like put 1, put 2, put 3, put 4. 0 is just saying, hey, you're just a replicated value. This is really just a cheap trick. You could just as easily create a separate code path only for replication, but we may as well. We already wrote the ability for a client to put values, so we may as well just make a special case for replicated values. See where it says up here, the comment 0 means insert locally. That means, because under normal circumstances, if I were to say put 1, then this would have the normal code path and say, hey, I'm not the right node to store this value, so it would just refuse to do it. So we had to make this special case. So now we've got our replication. And this is it. This is the replication code. It does the remote call. All right. So everybody might want to back up a little. I think I'm turning into Carrie. So anyway, so the replication occurs to these nodes. And let's see this in action. So I fire up the nodes and the ring state changes as we expect. Now our client is putting values in. But what's interesting is it's replicating all these values. So at first it was putting in 1 value, then it was writing 2, and then getting values from 1 node to getting values from 2. Now if you will notice, it took double the time to get values from 1 node versus getting the values from 2 node. That is almost exactly what you would expect it to be the case. However, since you've gotten a value from 2 nodes, you can be a little more confident that the value you're getting is the most recent one. And then, but there's a problem with what we've done so far, and it's this. So I have my values, baz bar qux. Let's see if I have my client that caused this. I don't. Anyway, so the point was, since I had gotten from 2, I actually received 3 values back, and I expect to receive 1. And the problem is this. The more copies you have, the more problems you have. Different versions on a node can conflict. Say I wrote one value for key foo to node A, and I write another value to node B, and I say, okay, read from both of those. And then it returns both of those values, but they're not the same. So what our code does is it creates something called a sibling. It will just return them both and then say, okay, it's up to you to figure it out. But there's something better we can do, which is called vector clocks. You can't rely on system clocks to be synchronized. You just plain can't. But we don't need a synchronized system clock. All we need is logical ordering to know which are the most recent values and which are the older values. So this is an example of vector clock. So say you have Alice and you have Bob, and they say, okay, Alice says, I want pizza, and Bob says, I want a taco. And then Alice goes to read the write and says, oh, Bob says taco, I said pizza, where did my pizza go? I'm going to update this value and increment myself and Bob, and then write taco pizza. So now when Bob does the get, he's going to know that Alice took his suggestion into account when coming up with the final value. This is just another view of vector clock. I'm not going to go into the implementation of vector clock right now, but the important thing to note is this, so you can increment just like we had shown before. We compare them, and it's 0. Now we increment Adam. Did V descend from V1? Yes, it did. Then we increment Barb. Is there a conflict? Yes, there is. Because what I did here was I had Adam incremented, I cloned it, so that, I added Barb, and then I cloned it so they're the same, and then I incremented them both independently of each other. And then if you compare them, it'll tell you, these are a conflict. The values that you attempted to give me are in conflict. So. And this is what a conflict looks like in our system. So here, it just returned both of our values along with our V clock that we implemented. It gives the value hello 1 or hello 2, but we have 2 different V clocks. So then the next thing our client does is it will resolve it and say, you know what, I wanted hello 2, and it sends the V clock with both C and B together so that the system knows that it has resolved the conflict. And this is what that client looked like, and that's why it slept. I'm sorry, I'm running through really fast right now, because I don't know, how much time do I have right now? All right, a couple minutes. We do have some problems with vector clocks. They do grow forever. But there are multiple ways of resolving conflicts. You can choose a value at random, and this is actually what some implementations do. Now they say we use system clocks, but that's effectively random because, as we said, you can't ever guarantee that multiple servers will ever have completely synchronized clocks. Siblings, which is what we do, and React, it's what we did in our implementation here, or some predefined resolution, and that's CRDTs. CRDTs, conflict-free replicated data types, commutative replicative data types. So what our problem is this. So if we have 2 services connecting to our cluster here, and then say A does a read and says, okay, get me the value of some counter. Now I want to write the counter, and it's 2. And B says, at the exact same time, read it. Okay, now add a value, increment. Now write it as 2. That A created a conflict. So when B goes to read it again, which one is it? Is the incrementation 2 or is it 4? It's actually neither. It's 3 because we had the number 1 and we incremented it 1 over here, we incremented it 1 over there, so we've got 3, but we can't ever pick it out of the data that's in there. So the solution instead is only store what the changes are and try to let the system resolve those changes on the back end if it can. So in this case, we just say +1 to the one that's already there, and we get a value out. There could have been a conflict. There's a conflict on both of these, but what happens is, so it took this +1, it created a 2 inside here. This had the +1. There's a conflict, so what it'll do is, it'll say, I don't know what to do with this +1, so I'm just going to return the 2 back to you guys and say, oh, there's also another pending +1. And that's easier to resolve because you can manually just take that 2 and that +1 and add them together and get 3. But you don't even need to manually resolve it. That's what a CRDT is for. CRDT counter, in this case, resolves it for you. I'm not going to go through all the details of the code. Again, you can read this because we're running out of time. But the interesting thing is here is that when you get the counter, if there exists multiple node objects, which means that there were siblings, it'll resolve them for you and send you a valid result. And the nice thing about it is we don't have to send in any sort of vector clock information at all. We just say, OK, I'm putting 1, I'm putting 2, I'm putting 1. We expect to get the value 4. And that is exactly what we'll get. We're going to skip the demo. You all, I hope, know how addition works. The response would have been 4. There's other types that we can do this with. We can do this with sets. We can do this with lists. If we have a set, we can say, OK, add a value to this set, subtract a value from this set. And then if there's any conflicts, the server is able to merge them itself. So we're going to skip through entropy as well. It's very interesting, but we are almost entirely out of time. Merkle trees, fantastic. I highly recommend looking up this information. What it effectively are doing is we're creating a hash tree, and then each of the nodes, each level of this hash tree that contains effectively a diff of what all of the trees are doing, it will then compare each level at a time so that it can actively repair these siblings that are occurring on the back end, and you don't have to actually repair them yourself. But I will do one more complex query, and this is actually the last thing, all right? We got 2 minutes? All right, MapReduce. And I'm going to do MapReduce because we've got this really awesome consistent system now, but you know, it's still just a key value store. How boring is that? You want to do more complex queries. And I want to do this because I want to show that MapReduce, is everybody familiar with MapReduce? Everybody used MapReduce? No one. OK, so really quick. If you're a Ruby programmer, this should actually be fairly straightforward because you're probably already familiar with these functions. You might not even necessarily realize it. So there actually is a function called map in Ruby, and there is a function in array called reduce. That's what MapReduce is. So what map does is it changes an array of objects from one thing into something else. It's mapping them one at a time to something else. In this case, what we're doing is say we have an array of hashes, and all we're doing is we're saying, OK, get the value out of the hash. So we've turned this array of hashes into an array of numbers, 1, 3, and 5. Step 2 is reduce, where we're saying, OK, we're going to prime it with 0, and we're just going to sum them all together, and we get 9. So it's iterating through all of this and aggregating a result. That's the reduce phase. The interesting thing about this is you can actually distribute it. You can actually say, OK, hey, you server, map these values, reduce it. You server over here, do the same thing. Map these values, reduce it. Give me the reduced result, and then re-reduce it, and then give me an answer. And this runs on the predicate, this works on the predicate that when you have like petabytes of data, it's way cheaper to send the algorithm to the data than it is to pull the data to the algorithm. And that's all you're doing. You're just sending it out there, and then you're getting the result back. It's up to the nodes that contain the data to actually run it. So we this is what our MapReduce is going to look like. It's really simple. It's really straightforward. We have a map function that just evaluates some function that it's bound to. MR is the name of our MapReduce command that we're adding into our node. If you notice, it says module MapReduce because, again, we're creating all these separate modules so we can add it into the node, and it adds this functionality to the node when we import it. So what it's doing is it's going to, up here where you see it says call maps function. That's down here. And that's where it will then remote call all of the nodes and say, hey, you map, you map, you map, you map, you map. And then it will just sit and wait and then aggregate all of the results. It also has to map its own results locally. And then it returns them, which then get reduced. And that's it. Oh, and that's the actual sends the socket out call. And this is probably my favorite part of this whole thing, is we can run MapReduce on our values. So we stuck a whole bunch of values in, then we said, OK, I'm going to count all the objects, and I'm going to sum all the values. That was relatively fast, distributed across 3 servers with a minimal amount of code. So this is what we've done. distributed, replicated, self-healing, conflict-resolving, eventually consistent key-value database with MapReduce in about 250 lines of code, which is effectively what React does, but it's considerably more lines of code, but it's Erlang, and we won't hold it against them for being implemented in that way. That was all.